This is Chapter 7 of Statistics for Psychology, and we'll be talking today about an introduction to t-tests. This is part 1, and in this we will be reviewing the key concepts and then going over the fundamental underpinnings of the t-distribution. So reviewing the main steps of hypothesis testing, we know that we've been working with z-tests in which we've been comparing a sample mean with a population that has a known mean and standard deviation, and that normal distribution is called the z-distribution. And so we've identified the populations and stated the hypotheses. Then we describe the comparison distribution. So in the case of the z-test, where we have an n of greater than 1, we're using the central limit theorem to determine the mean, spread, and shape of that distribution. In this step, we would draw the distributions if required to do so, and we know that we would base this distribution on the distribution of means when our sample is greater than 1, so we aren't comparing it anymore to the population of individuals. We would determine the cutoff points, and we would base that on the significance level, which is sometimes called alpha, but we've been calling it significance level or the p-value. And we need to know the tails, whether it's a 1 or 2-tailed test. Then in step 4, we would establish the sample z-score on the comparison distribution, which we do for our sample mean just in the same way as for an individual score, by subtracting the mean for the distribution of means from the sample mean, and then dividing that by the standard deviation of the distribution of means, or the standard error. And this is the formula. And all of that sounds like much more of a mouthful than it is. I hope you're finding that. And then we make our decision about the null hypothesis based on whether the z-value for our sample is to the extreme of our cutoff point. So in step 2, we'll be describing the comparison distribution. And we start by finding the mean, and we know how to find the mean. So I'll review that here because this will be useful. So first off, the calculation is, of course, to sum the raw scores and divide by n. Reminder about some of the symbols. X stands for an individual score. X bar stands for the mean for a sample. So you've drawn a sample out of the population, and you can express that mean as X bar, or you can also express it as a capital uppercase M. Both of them mean the same thing. Mu, when we see these Greek symbols, we're referring to a population. And so the symbol mu refers to the mean for a population with a known distribution. And the mu sign with a little m next to it means the mean for a distribution of means. That's what the little m stands for. It tells us we're looking for the distribution of means. In general, when you see a little letter in subtext after a symbol of some sort, it just tells you what the symbol is referring to. That's what the lower one stands for. What is this mean referring to? It's referring to the mean for the distribution of means. And we know from the central limit theorem that the mean for the population is the same as the mean for the distribution of means. So in this case, we just substitute in the mean we already know. So remembering also what we mean by a distribution of means. This is just the distribution that's created when the means are calculated and plotted from an infinite number of samples with a particular sample size. What we did in class is we drew out dominoes from a hat, and we did sample sizes of 2, and then we plotted the average number of points on each domino. And then we plotted that, and then we had a distribution of means based on a sample size of 2. And we knew that that distribution was going to be narrower than the population of individuals because it's less likely that we'll draw 2 tiles with an extreme score. And of course, whatever the sample size is, our distribution of means has to be based on that sample size. So the distribution of means for a sample size of 30 will be based on the presumption that we've drawn out in infinite numbers of samples of the size n equals 30. The second characteristic we have to identify from the comparison distribution is spread. We determine spread through the standard deviation and the variance. the standard deviation and variance are just different ways of expressing the same idea, because the variance is always the square of the standard deviation, and the standard deviation is always the square root of the variance. So the standard deviation is the measure for a spread in a population of individuals. And going way back to the start of the semester, you'll recall that we calculate it by summing the squared deviations, dividing that by n to get the variance, and then finding the square root of that number to get the standard deviation. What do we mean by sum the squared deviations? All the deviations is the difference between the mean and each individual score. So taking each score that came up in the sample, subtracting the mean, and then squaring all of those differences and summing them up before we divide by n. So you might think of it as like an average of the standard deviation. But we always, as you know, we always do that extra calculation. Instead of just taking the standard deviation and dividing by n, we always go up, square it to calculate the variance and divide that number by n, and then go back down, taking the square root. A little reminder about some of the symbology. When we have uppercase SD, we're talking about the standard deviation for a sample, which is these are known individuals that we've drawn out of the hat. Sigma is the standard deviation for a population with a known distribution. So when we're talking about this kind of conceptual idea, sigma, the population in general, and we can't probably name every individual who contributed to it, that's what we mean by the population. And then sigma with that little m next to it is referring to the standard deviation for a distribution of means from a known population distribution. And don't get confused with that little m. Whenever we see a little character next to a symbol of some sort, that small character is just telling us what the symbol refers to. So here we see sigma. We know that's a standard deviation for some sort of a population. For what population? For the distribution of means, that population. We can also call it, and this is where some people start to feel confused, we could say it this way, standard deviation for the distribution of means, or we could say standard error and use the acronym SE, or we could say standard error of means and use the acronym SEM. And remember, the variance and standard deviation are related, so once we know the standard deviation, we can take the square and we know the variance. And so and you can, this instruction, this calculation tells you how to get there either way, from the raw data or from the standard deviation. And again, just a little bit about the symbology. The symbols for standard deviation, if you see a squared next to them, then they're telling you variance. So SD squared is the variance for a sample. Sigma squared is the variance for a population. And sigma squared with this little m is the variance for a distribution of means. But we haven't yet calculated the distribution of means. All we've calculated is the distribution for a set of raw scores. So let's continue on with spread and use the central limit theorem to calculate the standard deviation for the distribution of means. And remember, once again, we can refer to it as standard deviation for a distribution of means using sigma with a little m, standard error, and standard error of means, all referring to the same thing. And this is the spread of a distribution. And the way we calculate that is we would first determine the variance, and then we would, which is basically squaring the standard deviation and dividing by n, and then we're going to find the square root to get the standard deviation, to get the standard error. The variance for the distribution of means is, again, the same relationship. The variance for the distribution of means is the square of the standard error. The standard error is the square root of the variance for the distribution of means. So all we do is to get the variance for a distribution of means. If we know the standard deviation for the sample, we just square it and divide by n, and then we have the variance for the distribution of means. A little quick quiz. If the standard deviation is 4, what is the variance? Think about that. Write down your answers if you want to check, because I'll put them up in a minute. If this variance, standard deviation squared, equals 4, what is the standard deviation? If the variance equals 9, what is the standard deviation? What is the difference between SD and sigma? A sample of 10 was drawn from a population with a variance of 40. What is the standard deviation for the distribution of means? What are two other ways to state standard deviations for the distribution of means? So if you want to take a moment to write down your answers, just pause. I'll go on. So standard deviation is 4. What is the variance? And that answer is 16, because we know that to get variance from standard deviation, we simply square it. Standard deviation squared is 4, and that is variance is 4. What is the standard deviation? Well, we know it's the square root of the variance. If the variance is 9, what is the standard deviation? And the answer is 3. We take the square root of the variance. What is the difference between SD and sigma? SD is the standard deviation for a sample, and sigma is the standard deviation for a population. A sample of 10 was drawn from a population with a variance of 40. What is the standard deviation for the distribution of means? And all we have to do is divide the variance. We have to take the square root of the variance divided by n. So that is the square root of 40 divided by 10, which gives us the square root of 4, which equals 2. What are two other ways to state standard deviation for the distribution of means? And that answer is standard error, or standard error of means. So, and finally, the last thing that we have to describe for the comparison distribution is the shape. Again, the central limit theorem is applied, and we know that the z distribution represents a normal distribution. We can use the z distribution as our comparison distribution if we have a sample greater than 30, or if the sample has been randomly drawn from a population with a normal distribution. We're now going to be working with situations in which we have a smaller sample, and if the distribution of the population is unknown, or if we're comparing two samples with each other and not with a known population. And so this is our introduction to t-tests, where we'll go over the conceptual underpinnings of the t-distribution. So we're going to learn today how to compare a sample with a population for which the characteristics of the distribution are unknown or unavailable. And we'll be doing in particular this first time around the single sample t-test, which is a test for comparing a single sample of individuals to a population where we know the mean, but we don't know the variance. And we also call this the one sample t-test. And then we'll do the dependent means t-test. And these are situations in which data from a sample of individuals is compared to data from the same individuals at a second point in time. We also call this the paired samples t-test and repeated measures t-test. We also call this, we say we use this with a within subjects design because we're comparing all data within subject. So if we have your score from test 1 and your score from test 2, then we're going to compare your scores, the scores within you for this design. So what's the problem? The problem is we don't know the comparison distribution. We don't know the characteristics for step 2, so we have to estimate it from the sample. So this is what we do know. When we estimate from a sample, we know that the sample will have similar but smaller variance than the population, but a shape that is similar to the population. So in the case of A, this is a sample, let's say a group of 25 drawn from this population. And you can see that the sample resembles the population in its basic shape, but we can also see that it's narrower. It's narrower than the population in general. So then if we wanted to infer characteristics of this population from characteristics of this sample, we know the variance is going to be a little bit different in the population, a little bit larger in the population. We know that in example B, here is the population, and here is the sample. And once again, we have the same basic shape. It's tall and thin. It's a steep sample, and we can see that it's a little bit smaller in its variance, or its standard deviation, its spread. And the same for example C. We see that our sample has a slightly smaller variance than our population, but the same basic shape. So we can estimate the distribution of means for the population sample. If the sample variance is small, the population variance will be small, and vice versa. A problem is that we have to take into account the fact that the variance in the sample is smaller than the variance in the population. If we simply calculate the standard deviation for the sample and extrapolate it to the population, we will systematically underestimate the variance for the population. So what we have to do, if we just did that, if we just said that the population standard deviation was the same as the sample standard deviation, we would call that an error. In some ways, we would call it a biased estimate of the population variance. Our estimate of the population variance would be too small because our sample's variance is smaller than the population. So we have to adjust the formula, and we adjust it by dividing by n-1 instead of by n. So you'll recall that when we calculated the standard deviation for the distribution of means, we took the variance for the population of individuals and divided by n. But now, when we don't know the variance for the population, we have to take the variance for the standard deviation, the variance for the sample, and divide by n-1. And this n-1 that you see is a really common function in statistics. It allows us to have a little bit more accurate an estimate when we're estimating populations from samples. So if we take a smaller denominator, we're going to take over for that risk of underestimating the variance for the population. That way, we would have what we call an unbiased estimate of the population variance. Now, what is it about this n-1? n-1 is called degrees of freedom, and it's very common in statistics. So what it means is that it tells us how many numbers are free to vary in a sample. So if we know the mean, and we know all the scores except one score in the sample, and that's the same as saying n-1, we can just use some math and figure out what that last score has to be. All of those scores can be whatever they want to, except the last one. Another example is just using this archer, and this archer wants to hit this target. And there are several factors. There are probably many more than I've listed, but let's imagine that there are 3 variables that can vary. The archer can stand farther or nearer or closer to the target, so distance can vary. The angle at which the archer shoots can vary, and the tension, how far he or she pulls the string back, can vary. 3 variables, or n equals 3. But once she chooses 2 of the variables, let's say she chooses her distance and she chooses her angle, then the 3rd variable can't vary. There's only one possibility that will allow her to hit the target if these other 2 variables, distance and angle, are set. So that's what we mean by degrees of freedom. And I'm going to see if I can stream to you this brief little clip that will explain it as well.
This is an introduction to degrees of freedom. The easiest way to understand the concept is to think about calculating an average, or a mean. Presume that you have 4 scores with a mean of 50. That means that the sum of those 4 scores has to come out to 200. So let's choose our first score. Well, it can be just anything we want. Let's say it's 70. So our running total at the moment is 70. Our second score can be anything we want. We're totally free to choose our second score. So let's say it's a 20, which brings our total to 90. Again, we're totally free to choose our third score, say 45, which brings us up to 135. And at this point, our freedom stops. We cannot have any choice on that last number. It has to be 65 because the sum has to come up to 200. So essentially, when we're doing the average of 4 scores, we have 3 degrees of freedom. If we had 10 scores, we'd have 9 degrees of freedom. We're totally free for the first 9 numbers, but the 10th number is forced on us. In general, when computing an average, if you have n scores, you have n minus 1 degrees of freedom. This same logic carries over when we're doing something like the related t-test, where we're calculating the average of the differences between the before and after conditions. Since we have n items, or n people who are participating in the experiment, that means we have...
And I'm actually stopping here because we aren't going to get into these dependent t-tests or within subject t-tests until next week. So that's not relevant for you to know, but I liked his little description of degrees of freedom.
n minus...
So the key differences that we'll note between the comparison distribution in z-tests and t-tests. The mean, we'll talk about this a little later. The same idea though, the comparison distribution will be the same. The spread, the variance of the comparison distribution, we have to estimate from the sample because we don't know what it is from the population. But other than that, we calculate spread in the same way as we did for z-tests. And the shape, we're no longer using the distribution that is the z distribution, but instead we're using the t distribution, which is just a distribution that has a little bit fatter tails to accommodate the fact that we're estimating the variance. So t distributions, unlike the z distribution, where there's one distribution and we can always know that the cut point for a p-value of 0.05 is going to be 1.64. We always know that with the z distribution. That's not the case in the t distribution, because the t distribution looks a little different for every degree of freedom, or for every number in the sample, we might say. So we have to always look up our t-values when we're doing a t-test, unless we're using a statistical program. So cutoff points are a little bit more severe in t-tests because we're taking into account the fact that we're estimating from the sample. So how do we do the spread? Well, we estimate from the population variance, and remember, the formula is exactly like calculating variance in general, except we're going to divide by the degrees of freedom instead of by n. Now, the symbol, by the way, for this, what we call the unbiased estimate of the population variance, is just this uppercase italicized s squared. And of course, you can already guess that the symbol for the standard deviation for this unbiased estimate of population standard deviation is just the s without the squared. So the calculation, you might recognize part of this. You might recognize this top part or this numerator, for example. Remember, we just reviewed when we calculate the standard deviation for a population of individuals, we take the sum of each score, represented by x, minus the mean, and we square it. And that's called the sum of squares. So we're still coming back to the sum of squares. Now this is like a month or 5 weeks ago. So think back to the sum of squares, SS. All it means is the sum of squared deviations. And so we're squaring each one of those deviations, summing them up, and then instead of dividing by n, we're going to divide by n minus 1. That's it. That's it. So we're taking the very same formula that we use to calculate the variance for a population, and the only difference is we're dividing by degrees of freedom instead of by n. And that is because, again, we're not interested in the variance or the standard deviation for the sample per se. What we're interested in is the population. And so we have to use an estimate of the population variance, and we have to account for the fact that we're estimating it from a sample. So calculating the standard deviation for the distribution of means, we do the same way then. So once we have that variance, we can take the square root and get the standard deviation, but it's the same thing. Once we have the variance for our sample, once we have the unbiased estimate because we've divided by n minus 1, then we have this. We have that standard deviation variance for the distribution of means that is unbiased, and that's what this S means, that it's unbiased. We would have sigma if it was a known population parameter. So the variance for the distribution of means is just the variance divided by n. Now this is where I think it can get really confusing, because you're saying, what? Come on now, we just divided by n minus 1. What's this dividing by n now? But remember, all we were doing with that n minus 1 was calculating the variance for the population based on scores of individuals. Now we have to calculate the variation for the distribution of means, which is based on the averages of an infinite number of sample sizes in order to get the variance for the distribution of means. So this will seem complicated. You'll work with it, and truly in time, all of a sudden it'll make sense to you. Oh, I see. We're just adding this step for this reason. So always keep your mind active while you're working with this, and then eventually it'll fall into place. So then we just do the same thing as we did when we were calculating for our z-distributions. We take the square root, and we'll get our standard deviation for the distribution of means, which is going to be S, not sigma, and not SD. It's not sigma because it's based on this estimate, and we don't base population standard deviations on estimates. And it's not SD because it's not representing the sample, it's representing the population. So this is the most confusing part for you, I think. So read this, and then look it up and read it, and then read it in your book, and then read this again, and it'll start to fall into place. So the shape of the comparison distribution is the t-distribution, and these are some pictures of it, and I also posted a nice little video. It's called the student t-distribution. Doesn't actually have anything to do with students. It has to do with the person who developed the distribution and the fact that he wasn't allowed to publish with his name, and so he just referred to himself as a student. The t-distribution has fatter tails than the z-distribution, so here we have the normal z-distribution in black. In this, let's see, this particular dotted line with dashes, we have a degree of freedom of 20, so our sample size is 21. And in this t-distribution with the dots, we have a degree of freedom of 2. So the sample size is 3. And we can see that there are very fat tails on this sample size with a distribution of 2. It's shorter and it has fatter tails. It doesn't look as much like the other distribution. When we get up to 20, the distribution looks a lot more like the normal distribution. And so there's not too much difference as we get larger and larger samples. But when we have those smaller numbers, the t-distribution is fairly different from the normal distribution. This is a little video that I won't share with you at this time. Oh, he wants to share.
Varying.
Well, we'll play it out just a minute.
Okay, so what we can do now is have a look at how that t-distribution looks in comparison to the z-distribution. And this is a t-distribution with those 4 degrees of freedom. And you can see indeed that it has fatter tails, and it's also less peaked at the top, right? So in other words, that extra uncertainty we have means our distribution is pushed outwards a little bit. We have more of the distribution in the tails. And you can see that if we drop the degrees of freedom even further, there's degrees of freedom being 3, being 2, being 1, which is just literally having 2 observations in your sample. So clearly when you have only 2 observations in your sample, you can't be that certain about that estimate of the standard deviation that you're using in these formulas, right? So the t-distribution is really going to flatten out hard here. If we go back in the other direction, there's 2 again, 3, 4, and we can keep pushing to see what it looks like when the degrees of freedom gets significantly higher. And I'll stop at about 20. So you can see what's happening. As the degrees of freedom gets larger and larger, this orange curve here, which is the t-distribution, approaches the white one, which is our z, or standard normal distribution. And that makes sense too. If you have a sample of 20 or more, you're starting to become quite confident about your estimate of the standard deviation, right? You no longer need to adjust that much for this lack of information that you have. So eventually, as the number of observations and thus the degrees of freedom keep increasing, the t-distribution will eventually become, at the asymptote, the z-distribution.
All right. So just a little bit more here. We lose accuracy when we estimate the unbiased estimate of the variance, so we use a more severe cutoff point. So you know that a one-tailed z-test with probability less than 0.05 uses a cutoff point of 1.64, and that's regardless of n. Using the t-chart, a one-tailed t-test with p less than 0.05 uses a different cutoff point for each degree of freedom. So if you had a sample, in this case they're using degrees of freedom are 15, meaning there's 16 in the sample, and so this is this blue shaded area, and they're using a one-tailed test, so we're looking on this half of the chart, and we're looking down the 0.05 column, and the place where those cross, the degrees of freedom 15 with a 0.05 cutoff point for a one-tailed test is at 1.753. So if we're doing a t-test, instead of using 1.64, we would use 1.753 if our sample was 15, if our degrees of freedom was 15. The table continues to show larger sample sizes, and coming to smaller, if we only had 10, we would have to use for a one-tailed test a cutoff point of 1.813, or for a two-tailed test, we'd have to follow it over to here. And you can see that the cutoff point for a two-tailed test at p.05 is 2.132. So this is how you use the chart, which is in the back of your book and which I've also posted on Blackboard. So in summary, we use the t-distribution when we want to compare a sample, but we don't know the distribution of the population, or we want to compare two samples. And it's especially useful when we have small sample sizes, as it offers a conservative estimate of the variance.